in a metric space X, let's say X is a metric space, we can define the closure of a set. Okay, so let's say we have a set E in our metric space, okay? And then we are going to denote by E prime the set of limit points of E. Okay, these are the set of limit points of E in X. Okay. Once we, with this notation, then the closure is called E bar. This is just the union of the set and the limit points. Okay, so we are taking both of them together. So for example, a very simple example, if we have an open interval AB, the limit points here, well, let's go straight to the closure. The closure of this open interval is going to be the closed interval. Okay, because we have all the interior points are limit points, but also the endpoints are limit points, because we can have sequences of points going to the endpoints. Okay. All right. So this is the definition of closure. So we have a theorem. Sometimes this is very useful because it allows to show that that some set is closed. Okay, you will see what I mean. So let's, again, the same framework. Let's say X is a metric space. Okay, and E is a subset of X. Then this is like the user agreements that we usually scroll down and don't read, but we should read the context of a theorem. Okay, in this case, we have that A, the closure of E is closed. Okay, so the closure of any set makes it closed. Okay, you can take an open set, add the closure, becomes closed. Of course, you may be wondering what happens if I take the closure of a closed set. So in that case, nothing happens. Okay, if and only if, whenever a set coincides with a closure, the set was already closed to start with. So for example, this is a way that we can show that the set is closed, showing that the set coincides with its closure. Okay. And then the third property says that if we have that the closure is contained in a set F, and this happens for every closed set F in X, and then the last one that says that the closure is a subset of every closed set F contained in X. Of course, the sets that contain E. Okay. Oh, wait, I'm forgetting something important. Of course, the importance of this is that by A and C, the closure of E is the smallest closed set that contains E. Well, actually, I should say the smallest closed set in X that contains E, just in case. Okay, so this means that the closure of every possible closed set that you could take that contains the original set, the closure is the smallest. So let's prove the theorem. Let's start with A. Here we want to show that the closure is closed. So let me show actually that the complement is open. This we need to do every time, like play with the statements. Like maybe there is some property, like in this case, that if you take the complement, you can work with open sets, and maybe that's more convenient for you. In this case, it's going to be more convenient. So let's say we have this is a very naive sketch. Okay, let's say this is our E bar, and let's say we take a point P that is in X, and let's say that is not a point in the closure. Why am I doing this? I want to show that the complement is open, correct? So if I want to show that the complement is open, I need to take a point. A point in the complement is a point P that doesn't belong to the original set, to the closure. And then to show that it's open, and I need to show that there is some neighborhood around P that is not contained, that doesn't touch or all the closure of E. Okay, so that's our goal. So let's get to it. Because we know that P doesn't belong to the closure of E, which is E union E prime. That means that P is not an element of E, and also not a limit point. This is by definition, okay? The limit points of E, those are the points in E prime. So because it's not in E prime, that's it. But now, what is the definition of limit point? So some point P is a limit point of the set E if every neighborhood of P that I take contains one point Q different from P that is not in the original set in E. Okay, so that means because it's not a limit point, that means so a limit point would be some point X such that for whatever neighborhood I take, there will be a sequence of points. Okay, there will always be some point for whatever neighborhood, no matter how small the neighborhood, there will always be some point in that neighborhood. Okay, if the point is not, if the point P, sorry I wrote X, but it's P. If the point P is not a limit point, that means that there exists some neighborhood. As we shrink, there will be some neighborhood that contains no more points. Okay, so the sequence doesn't stops. Okay, there exists a neighborhood of P that contains no points of E. Okay, and this is it. We have been able to show that there is a neighborhood N that does not intersect E, and that means that the complement of the closure is open. Okay, and because it's open, then the closure is closed as we wanted. Okay, so that is A. This proves there are a few techniques that we can learn. One is, first, always pay attention to the definition, but always the results we are proving, you can use them. Okay, so sometimes a statement about closed sets can become a statement about open sets, just taking the complement. Now B, here we need to show that E coincides with the closure, with its closure, if and only if E is closed. Okay, there. So it's a if and only if. We need to check both implications, but one of them is very easy because we just said by part A, E bar, which is equal to E, is closed, and that's it. Okay, so now to go back, we need to assume that E is closed, and then we want to prove that E coincides with the closure. Okay, but here's the thing, because E is closed, then E prime is contained in E. That's the definition of closed, okay? E is closed if every limit point of E is a point of E. Okay, that's exactly what I'm writing here with E prime contained in E. But then that's it, because notice that the closure is E union with E prime, but because E prime is contained in E, the union is E. Okay, it's like if I take something like this is E, this is E prime, so the union is the bigger set. Okay, all these, I'm doing these pictures just to get the idea, but in analysis, this is the art of getting the right intuition from the wrong picture. Okay, these pictures have nothing to do with reality; they are just to understand. And we are one more to go. So C, E subset of F for every F in X closed such that it also contains E. Okay, so in this case, if we have E contained in F and F is closed, okay, then because it's closed, F prime is also contained in F. Okay, and that means that E prime is contained in F. Okay, once we know that E prime is contained in F, then we must have, because E bar is the union of E, which is contained in F, and E prime, which is contained in F. Let me write that down. So this is E union E prime, but both of them are contained in F, so the closure is contained in F. And with this, we're done with the proof here.